let's try and see what happens if we add values I plus 1, I plus 2, I plus 3 until there is a node split. This is actually how InnoDB works. So in the first case, we add these values. Once we add I plus some value m minus 1, m is the I plus m is when the node split occurs. The node is full, and next a new node is created, and the new node will hold only one value, and that is I plus m. So if you make many consecutive inserts, and that's like more than 15, I believe, a new node is created, and this node has only one value. It's not split in half. The other case, when there's only one value to the right of I, and we add values I plus 1, I plus 2, and let's imagine that we don't insert a value over k, then there's a node split, and the new node to the right will hold two values, I plus m and k, and the node on the right will have one empty place. We'll have room for one more key. Finally, when there are several keys to the right of I, and you add the values, then all the keys but the first one are moved to the new node, and the first key, k1, is left in this node. So let's see how we can use these cases of node split to execute the attack. Now, this is a summary or an outline of sketch of our algorithm. It goes in three phases. First, a setup phase where we make certain surgically selected inserts in order to prepare the tree for our insertion algorithm. This will only take a few inserts in complexity. This is not what dominates the complexity of the attack, but we need to execute the binary search. We need the configuration I put here in these two nodes, which is, we know one value, or the attacker knows one value A. He knows there's no other key in the node but A, and in the key to the right, there's the key we are searching for, the value that we want to steal from the database. We don't know which value it is, but we know that there's a node that starts with K. And the next value to the right of K is B, which is also known to the attacker. So the attacker knows A and B, and he knows that in between them there's a key K, which we want to extract. And our setup algorithm does precisely that. It arrives to a stage where you have the tree in this configuration, and K is the first key. And then you can execute the binary search algorithm, which will loop a procedure that at each time halves the size of the interval between A and B. B minus A, it's halved. And also this configuration is maintained. So A will be on the left node, and the right node will have two values, K and B. Well, there might be other values to the right of B, we don't care. And the size between B and the B minus A will be half of what it was before running this procedure. So we will run this procedure until B minus I, which are known to the attacker, are smaller than the size of the page. That's n. For example, in MySQL, in the experiments we made, it was 574. Once you reach to an interval of that size, then we start searching for the key manually. In A plus 1, A plus 2, A plus 3, you make these inserts until you get an error, and this will mean that you have found K. So I'm going to explain now how does the binary search algorithm work. I cannot get into the details of the setup algorithm, but this is explained in the paper, and for this talk, let's suffice that the setup algorithm will only use the cases 1, 2, and 3 I mentioned before. So let's see how the binary search works. This is almost a proof that our algorithm succeeds, and it will help to estimate the complexity of the algorithm. So let's assume that we are in this situation. K is between A and B. A and B are known to the attacker. There are no values between K and B. K is the smallest value in a leaf. And we start inserting a plus b divided by 2, a plus b divided by 2 plus 1, and all the values that divide this algorithm in half. Now, two things can happen, or three things can happen. Either k is to the left of a plus b divided by 2, it might be on the right, or it might be equal. If it's equal, then we've won. We found the key. So let's see what happens if it's smaller or larger. In the event that k is larger than a plus b divided by 2, and we make inserts a plus b divided by 2, plus 1, plus 2, plus 3, and so forth, we will eventually split the node, and the node will be split in this way. This is the case 1 I mentioned before, and if you recall, the new leaf created had only one value, in this case the last value inserted, which is I plus n minus 1, and the leaf on the right remains unchanged. So we are again in the same setting as before. We could take A as I plus n minus 1, the size of the interval is halved, and we can continue executing this. Now it should be noticed that in this case, inserting a plus 1 until a plus n minus 1, we made exactly n inserts. Now, we are going to use this n, because if k is smaller than a plus b divided by 2, then we are in this situation. K is to the left of I is I plus b divided by 2, and we add values, and we end up in this situation. There's a node on the left that remains unchanged, holding only the value a. The node on the right has the value k, the value I, and other values to the right. But essentially, we're interested in I, k, and a. And also the fact that here we made only n minus 1 inserts. So the attacker doesn't know anything else, but if the attacker knows when there's a node split, he knows in the earlier case the node was split after making n inserts, and here he knows there was a node split when he added n minus 1 inserts. So there's a difference here, and he can exploit this difference, because this difference will tell him if k is smaller or bigger than a plus b divided by 2. So this is how the binary search algorithm works. If we make n inserts, then we set a to a plus b divided by 2 plus n and run the algorithm again, else we set b to a plus b divided by 2 minus 1. And we can repeat this procedure because we are, each time it finishes, we are in the same configuration as before. So that's it. Each run will require approximately n minus 1 inserts, and by making these n inserts, the interval containing the keys halved. But in order to do this, to execute it, we need to detect splits. I mentioned split detection is one of the requirements of our algorithm. And split detection is very specific to the configuration and the instantiation of the database you are using. So I'm going to tell you about our experiments and how our split detection algorithm is robust, in the sense that it can handle some changes and it will work all the same. So about the noise. In most of the cases, if you measure the time taken by an insert that produces a split and an insert that doesn't produce a split, you can differentiate one from the other. One will take about 2 times the time as the other one. So in the average, you can differentiate node splits, inserts that produce node split from inserts that do not. However, we require a little more. We need accuracy to be perfect and detect node splits always. So there are some indistinguishable cases, but we know that speaking about the average, there is a mean value for inserts that do not produce splits, and there's a mean value for inserts that do produce splits. In our case, I believe it was 32 milliseconds for inserts that didn't produce splits and 70-something for inserts that did produce splits. So in the average, they can be differentiated. And we made this experiment I put here before. We inserted consecutive values, and distinguished all the values that were bigger than this threshold value. So maybe there was 32, 33, 45, and then one insert took 85 milliseconds. So we stored the order of this insert. And we did this with all the values. And we measured the separation from one insert to the other, from one insert that took a lot of time from another one. Let's say that we take the ith insert, the I plus nth insert, and the I plus 2nth insert, and let's assume that they are all bigger than the threshold value. Then, this is only statistical evidence. We proved in our experiments that if all these values were bigger than the threshold, then with 100% probability, this meant that these inserts were produced by node splits. Because there were other values that took more time than the threshold, and yet they weren't generated by node splits. So here is a sort of a split detection algorithm. Let me explain. Let's say that we get values I plus n, and I plus 2n, and they are all bigger than the threshold value. Then we write this into a table, and we say this is case 1 because node splits took n inserts, and we know that in case 1 of the cases described below, node splits take n inserts. In the other case, they take n minus 1 inserts, so this is case 2. And you can build a table with all the differences in the node splits and compare this against the values you get over the threshold. And in our experiments, it worked to detect the node splits always. So how our split detection algorithm works, you start with a value I, and you make consecutive inserts, and when the algorithm finishes, it will tell you either if the key k is on the left or on the right. Mainly if you're in case 1 or in case 2, case 3, or a combination of the other cases. We need to differentiate case 1 from the other cases. Now, this algorithm, of course, is not deterministic. It will not work always, but it always worked in our experiments. However, we need to mention that sometimes it didn't take 2n inserts, but it took a little more. So maybe there will be a lot of noise, and this I plus n and I plus 2n will not be located at the start of our insertion strategy, but maybe further. So instead of making, let's say, 1,000 inserts to detect one node split, maybe you have to make a few thousand. And the good thing about this is that with absolute probability in our experiments, when the algorithm says it detected a split, then the guess is correct. However, false positives can happen, and the algorithm might take a little more than 3 times n inserts. So now we need to combine the algorithm, the binary search I mentioned before, with the split detection algorithm I just described. And this is easy. We need simply to establish if the key is smaller or bigger than a plus b divided by 2. So if you recall, there was a slide almost like this one, and this was when k was smaller than a plus b divided by 2, and we made n inserts. Now, let's imagine that when inserting I plus n minus 1, we do not